Okie dokie. We're going to find the electric field at point P on the axis of a charged ring, and P is right here. A distance, this is the center of the charged ring, a distance x away from the center of the ring. And this ring has been drawn with an awesome 3D perspective that we've seen before. And we are in the ring. Let's describe the ring. The ring has radius r and charge q. There's a shocker. Haha, shocker. That's funny because it's charged. And we want to find out the field at point P created by all this charge on this hula hoop. So, how do we do it? We break the hoop up into infinitesimal charge elements with the calculus pizza cutter. And there are a few of them, dq, and I'm going to pay attention to the one that is in the plane of the board, which is at the very top of this loop, that dq right there. And I'm going to look at the field element it produces at point P, and that field element is going to be directed straight away from that positive charge dq. So I've got a little bit of electric field here, dE. And then I'm going to sum all of the fields created by all these little bits of charge. But before I do that, I don't want to add up a whole bunch of vectors as we discussed in class, because that's a pain in the butt. And so I'm, first of all, going to recognize that I only care about the x component of this vector. So let's draw that in. Here's dEx, because all the non-x components, all the y and z components, if you will, this is, I'm going to call that dEy, they all cancel because for this little charge element at the top, there's a charge element 180 degrees away from it, dq down here, which creates a field at this point. I'm going to draw this and then get rid of it. Creates a field element at point P which has the same x component as this one that we're interested in, but a y component, dEy, that cancels. Here's the x component that it has. That cancels the dEy from the piece at the top. So all the components perpendicular to the x-axis cancel out. I'm going to get rid of those. I hope. Go away, go away, go away, go away, go away. And so all I want to do is find the x components. So I'm going to write that I want E at point P is the integral of dEx. dE itself, what equation can I use for that? Well, this is a point charge up here. And so I will use the point charge formula, which is, I'm going to still use K instead of 1 over 4 pi epsilon naught. K Q over, that's dQ over R squared, where R is this distance from dQ to point P. And then, to get the x component, I say that's theta, and the x component is dE, that stuff we already wrote, times cosine theta. And theta, of course, is hiding over here because those are vertical angles, the two thetas that I just drew. And so cosine theta, because I don't want to be introducing another variable here, cosine theta is, last time I checked, adjacent over hypotenuse. Adjacent is x, hypotenuse is r, and so cos theta is x over r. So the field is integral of dEx, which is dE cos theta, which is k dQ over r squared. That's the dE times cos theta. Cos theta is x over r. And I want to express r in terms of things that we have already defined, such as, this is little r, and little r is the hypotenuse of a triangle with x and big R as its legs. So little r squared is x squared plus big R squared. And we're almost done, actually, with the ring. K dQ times x over little r, this is down here is little r cubed, and r squared is that, so I'm going to end up with x squared plus r squared quantity to the 3/2 power. And I hope that's right. And so now we get to integrate, dance with the music, because, and this is easy because k is a constant, x for this particular point P is a constant, big R is a constant, all those constants come out, and I get kx over x squared plus r squared, all to the 3 halves, integral dq, and what's integral dq? It's all of it, which is q. And so I can just write E equals kx, big fat Q over x squared plus r squared to the 3 halves power, and that makes me happy.